All right, we'll go ahead and get started. Um, so I'm feeling a little better today, but I'm still not 100%, and I get very exhausted very easily, so hopefully I'll be able to hold up here. I'm highly contagious, so no, I don't. I hope not. No, I mean I've done everything I can to, yeah, I'm trying. I'm not going to cough on you or anything. What's that? What's that? The Norton? I don't know. I'm not quite sure I believe that the Norton has done anything to help me. Um, let's take a look at this. Last class we started talking about polar coordinates, and what I was trying to get you to see is that to get to a point in the XY plane, normally we have an X coordinate and a Y coordinate, that we have a new way of looking at it. That instead of going out X and going up Y, you rotate by some angle theta, and then you walk out a certain distance. So if I change my radius, of course, I go out further, come back in. And if I change my theta, I go around that part of the circle. Okay, so that was the idea. It's just a different way of looking at this. The relationship between Cartesian and polar coordinates was that, from that picture you can kind of see this, that x squared plus y squared has to be equal to r squared because of the Pythagorean identity. X was r cosine theta. We did that by talking about what's cosine theta off that picture and then solving for x. And then what's sine theta? It's y over r, and then solving for y. And then we talked about the angle, right, coming from the arctangent. We did that last time. And then I also went on to talk about, well, if we restrict our theta between two numbers and our radius between two numbers, then we can actually create these regions that are circles. Okay, like that would be a region where my radius is between, let's say, 0 and I don't know what it is here, and then my angle's between where and where? 0 to 2 pi, right? But I could also bring that angle back, or that's my radius. Oops. Bring that angle back and maybe go, somewhere. I'm trying to get it to be 3 pi over 2. Right? Now my angle's between 0 and 3 pi over 2. I could change my angle here, and then I could change my radius, and then I could also change my inner radius. So now your angle's between two things, your outer and inner radius are between two things. And these are what we call, it seems kind of weird, but we call these like rectangular polar regions. Rectangular in the sense that both variables are between two fixed constants. The picture isn't rectangular, but the restrictions there, because they're between two constants, it's rectangular. All right. Now the rest of this, I stole this from my calculus class, my Cal 3 class, so I can't, can't really go into the rest of it. So I'll just pick up with our notes for today. All right, here we go. So we know that we have those relationships for polar coordinates. Do you want me to write down all those things? X squared plus y squared equals r squared. We're okay with it? All right. Polar coordinates. What we're going to wind up doing to start here is look at some graphs of polar equations. A polar equation, or a polar curve, I should say, have the form r equals some function of theta. All right, that's the big equation, I guess, that we have here. Here's the idea. We have the polar axis, right? Remember I talked about this last time? The polar axis is the x-axis in the positive direction, right? And if I give you an angle, right, then tell you to go out a certain distance at that angle, the distance you go out, like I'll just make one up. Let's say at 0 degrees, so here's theta, here's r. At 0 degrees, let's say it's 2. So that means you'd walk out, like pointing out the polar axis, you'd walk out 2, right? You get there, you stop. And that's where your point would be. Okay, so you would have that, right? Then let's say that at pi over 6, I want you to be at 1. That means I rotate by how much? 30 degrees, right? So I rotate 30 degrees, and I walk out how far? I walk out 1. So it's not 30 degrees and then go out 1 on the x-axis and up. It's rotate and then go out that distance 1. So I'd be somewhere around here, wouldn't I? Let's just say. And then maybe at pi over 4, I want you to be at 3. So at 45 degrees, I want you to be way out at 3 now. So I don't know, 1, 2. I'm just eyeballing this. Maybe it's around there. Right? And I could keep doing this, and you'd start, if you start connecting these points together, you have a curve, don't you? But I'd have to tell you exactly where you need to be at every angle, right? Not just these, everything in between also. So the radius here, if the radius is some function of the angle, it's called a polar curve. I'm not giving you the function here because I'm just making up. I just want you to see the relationship that you tell me which way to aim, and then tell me how far out to walk. If how far out I walk is a function of the angle, then it's called a polar curve. And I'm going to give you some examples. Maybe this one would look like this. Again, I'm just making this up. You know, maybe it does something later. But it starts to draw a curve, doesn't it? Okay, so let's talk about specific examples of polar curves. Here's your first example of a polar curve. I'm going to define R to be 3. And what I'm saying is that's my function of theta. It's a constant, isn't it? What you'll notice there is that 3 does not have theta in it, does it? Therefore, it doesn't matter what angle I'm at. At every angle, I'm supposed to walk out how far? 3. So what is it? It's a circle. Radius 3. It's a circle, radius 3. Okay, because what I'm telling you is that, remember, R is how far you walk out, right? I'm telling you to walk out 3, no matter what your angle is. See, because there is no theta in this formula, it's just saying, look, point out what angle, any angle, doesn't matter, walk out 3, walk out 3, walk out 3, walk out 3, walk out 3. So this is what a constant function looks like in polar coordinates. It draws a circle. All right, how about this one? Example, R equals, I don't want to do theirs yet. r equals 2 sine theta. R is 2 sine theta. So the way we're going to do this, we're going to try and do it with a t-table, just to see what happens. Here's theta, here's r. Let's pick some common angles that we know the value of sine. 0, okay, so at angle 0, we have 2 sine of 0. What's sine of 0? 0, right? Okay, now over here, I'm going to draw my graph. At angle 0, right, so when I'm pointed out the polar axis, I'm supposed to walk out how far? 0. So I'm just going to be at the origin, right? Now, let's walk out. I mean, that's not walk out. Let's change our angle. Let's go pi over 6. Okay. So if we go pi over 6, 2 sine of pi over 6. What's pi over 6? What's sine of pi over 6, I should say? 1/2 times 2 is 1. So you get 1. Is that all right? So now, now I have to realize where pi over 6 is. So I'm aiming out pi over 6, which is 30 degrees like this. I'm aiming out that direction, pi over 6, and I need to walk out 1 unit, right? 1 unit. And I haven't really said what 1 unit is right now, so I'm just going to make it up. I'm just going to say that this is 1 right here. Okay? Now let's go, you want to go pi over 2? Let's go one more before we go pi over 2. Let's go, how about, since we did pi over 6, let's go either pi over 4 or pi over 3. It doesn't matter to me. Do y'all care? Let's do pi over 4. What's 2 times sine of pi over 4? Well, sine of pi over 4 is root 2 over 2. So 2 times root 2 over 2 is just root 2, which is going to be 1.414 something. So it's almost 1.5. So when I'm aiming 45 degrees, I need to go out almost 1.5, which is going to put me, like there's maybe 1, I don't know, we're eyeballing this, maybe about there. Let me see if I can connect real quick. I want to show you something. You won't need this, but just so you know it exists. Polar graph paper. Have you ever seen polar graph paper before? This is what polar graph paper looks like. What it is, you know, you've got your origin, and then it gives you a bunch of angles. So what you do is, you know, we'd put our 0, 0, then at our 30 degrees, we'd walk out, and each one of these is a unit. So we would walk out 1, right? The next one we would have gone 45 degrees, isn't even on here, but it's halfway between 40 and 50, and you would have gone out 1.4. And then you can use this to graph something. Just so you know it exists. It's polar graph paper. The protractor? That's what. Protractor. Yeah, I mean, I guess you could use that also, you know, but this one is like you print it out and you draw on top of it. So it just makes it easier to get you don't have to figure out what those angles are. It's all here already. Just so you know it exists, that's all. Okay, so now the next one, let's go ahead and do pi over 3. Okay, 2 times sine of pi over 3. Sine of pi over 3 is root 3 over 2. So this would be root 3. What's square root of 3? 1.7 something. So at 60 degrees, we're at 1.7. So almost 2. This would be 2. So probably be, I don't know, somewhere around in here. Again, I'm really just eyeballing this. I'm not doing a perfect job. And then let's do pi over 2. So 2 sine of pi over 2. Sine of pi over 2. 1. 2 times 1 is 2. So we'd be up at 2 here. If that's 1, then that would be 2. So we're aiming straight up. We walk out 2. Make sense? Well, now when we come back around, if we plug in, let's go 30 more degrees, we'd be at, where is that? My brain's not working. No. Just excuse my brain for a second. Pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 2 pi over 3. Did you say that? Who said that? Okay. So the next one, if we did that here, we would actually be, sine of that would be the same as on the other side, so it would be back here. Oh, it's a little low. And then everything else would still be the same. So it'd be like in here, and then it'd be back down here. Actually, if you put it all together, it's going to be a circle. Like this. It's not good, but it's a circle. The radius is 1. Okay? It's very odd that that works out that way, but that's what it is. So let me show you how we can convince ourselves that this is a circle. Okay, watch this. I want to take this equation down here. I want to try and convert it to Cartesian. Now you can't always do this easily, but with this one you can. Convert it to Cartesian. So what we know right now is that r is equal to 2 sine theta. And the only thing that we have to go off of is this. X squared plus y squared must equal r squared, right? We have that x is equal to r cosine theta, y is equal to r sine theta, right? So what I'm going to do is I'm going to take, well, we also have the theta is arctangent y over x. I'm going to take this equation here because it has sine in it, and I'm going to solve it for sine theta. What would I get if I solved that for sine theta? Y over r. So can't I rewrite this equation as r equals 2 times y over r? And now can't I multiply both sides by r? R squared equals 2y. But what is r squared? X squared plus y squared equals 2y. Don't I have an equation now that has x's and y's in it? No more r's, no more thetas? Okay. X squared plus y squared minus 2y equals 0 is also that same equation. I can complete the square on y squared minus 2y. Remember how to complete the square? Take that negative 2, divide by 2, square it, add, subtract. So this would become x squared plus y squared minus 2y. Half of negative 2 is negative 1, squared is 1. Add it and subtract it. And then the 3 terms here can factor in to be what? Y minus 1 squared. Now we still had the minus 1 there, didn't we? Move it to the other side. So we have x squared plus y minus 1 squared equals 1, don't we? And if you remember, the general equation of a circle is x minus h squared plus y minus k squared equals r squared. That's the general equation of a circle centered at HK, radius R. So the center of our circle is x minus what? Well, 0. So 0, y minus what? 1. So 0, 1 is our center, and the radius is 1. So if you go back up to that circle, the center of that circle is where? 0, 1, and its radius is 1. So that just confirms that it is what it was looking like it was going to be. But like I said, it's not always easy to convert from polar to Cartesian. All right, so that's an example of how to sketch one by hand. They kind of, as the next example will show, it's not easy all the time. So with this example, r equals 1 plus sine theta. We could go through and sketch it, but I'm just going to show you what it is. I'm not going to go through a t-table. This is done in your book. It starts out, it goes like this, and then it comes back around, comes back, comes up here, does the same thing over here. Something like that. It's called a cardioid, like cardio, because it's shaped like a heart, flipped over, but it's heart shape. Cardioid. But if you made a t-table and started plugging in points, you kind of see that. That is not a circle. It's not anything obvious in Cartesian. So let me just show you why it would be so hard to convert this to Cartesian if we tried. I would try and replace my sine theta again by what? 1 over r? Or y over r? And then if I tried to multiply both sides by r again, I would get r squared, but then here I would get r plus y. R squared is x squared plus y squared equals r plus y. But see, the r is still there. So now I try and get that r out of there using something else. But the only other thing I have with r in it would be have a theta in it. Unless I did x squared plus y squared equals r squared and took the square root. So I could replace r with square root of x squared plus y squared plus y. That would be okay. But see, that's not an obvious, that's not something we look at, oh, that's a circle. So it's converted to Cartesian now, but it's not something we can say, check off our list and be like, oh yeah, we know that. We've seen that all the time, you know. Okay, any questions? Yeah. Well, I really hope so today. Let me see. I am recording, and that little thing down there is registering, so we should be okay. All right, now, yeah, last time I didn't even record. So, oh yeah, hey, here it's people who didn't see this earlier. That was the cycloid that I did. Last class I didn't have my jump drive, remember? My computer science people, that's the code for it right there. What's that? I need someone to I need to take a class on Java. I did a where's my I did something. I've been working on it. Oh Jesus. What the hell? Wow, that's ridiculous. Okay, let's see, 6, 7. This is what I tried yesterday, but I'll tell you what I'm doing while I'm doing this. I set up, you know, the stuff that I've been showing you. Wolfram Alpha doesn't do all that animation stuff, right? So everything I do in Mathematica. Well, the only way you can do it see it yourself is if you download their player. But they have a way that you can put it on a web server. So I'm using my computer at home. Ah, what the hell? Thank you. For right now, I'm using my computer at home as a web server. One of my spare laptops. And oh, I see, I misspelled something. Here it is. So this is what so this is being served off of my laptop at home, but I actually had put that cycloid in here. So you can click this and you can do this. But here's the problem. It uses Java, but you can't, it doesn't, I guess Java, you can only have it update, you can only take snapshots. So, you know, like the picture I had, the ball looked like it was rolling. I can't get it to roll. All I can get it to do is per frame, exactly. So I can move it around, but I can't. Well, I don't know. See, that's the thing. I'm not sure if the limitation is Java or if it's all that's happening basically is that I'm sending the command from the web to the kernel on my laptop. It's returning an image. And it just doesn't do that fast enough to make it look like animation. But why am I showing you that? Oh, because Java. Yeah, I need to know Java. What was I going to do? Oh, I wanted to plot. I wanted to show you how to, I wonder if Wolfram Alpha will do a polar plot. Let's see if Wolfram Alpha will do it. I know my computer will do it. Let's see if Wolfram Alpha does. What do y'all think? Think so? Did y'all see that new, that car, the P1? I forgot the name of who makes it, but it's over $1 million car. I think it's like 900 horsepower. It's crazy. Come on, let's go. Okay, so let's plot. Let's do that one that we just, the cardioid. It was, so I'm going to say polar plot, and I'm going to say 1 plus sine, and I guess I'll put theta in here, but I don't know. What do you think? Hey, I'm impressed. There it is. So you can have Wolfram Alpha plot you some stuff. And the book goes through and talks about some of the crazier stuff you can have out there. Here's another one. Cosine. See if we do cosine 2 theta. So I'm doubling. Remember, if you double inside, then what it does is you get more periods in there. Okay, by doubling it. So what happens is, or actually, you know what? Let me change it to sine. Let me change it to sine instead of cosine. It's not going to look much different, but you remember how we were going out and we were trying, the one that we did a while back, we drew the circle in the top half, right? Remember that? We drew that circle. Well, this one, what it does is by having two theta in there, it tries and goes out and draws a whole circle, but only in the first quadrant, or in that first polar region. And then it goes around and draws another one, and then another one, and then another one. And then let's see if they gave me the domain. See, this is from 0 to 2 pi. So if I go, I think I can tell it from 0 to pi instead. That's what it does. But if I change it from 4 theta, 2 theta to 5 theta, or 4 theta, let's see what happens. See that? You want me to go to 2 pi? It's going to start drawing on itself again, I think. Oh, no? Look at that. What you don't see in this is how it's drawing it, right? You're not seeing that point where it's moving. See, let me back this up. If I go from 0 to, let's go pi over 2, then it draws that part. So it looks like what happens is it goes out and maybe comes back down like this and goes like that. And then maybe if I add more, let me cut it and see what that does. Okay, so that just got me that one leaf of it. If I go out to pi over, I don't want to go that. If I go just pi, then we had this, which we saw, right? So we said it looked like it went like this. Looks like it went like this, and then came back down. It looks like it probably goes up and comes back down like this. And now if I keep going, right? Yeah, I mean, but it's moving, and you can almost look at it as like a point moving around. And then but it's not doing it. It's not doing like one quadrant at a time. It's jumping around. And now if I went out to, let's go 3 pi over 2, see where the next one would be. Yeah. So it looks like, let's see if we can follow it now. It looks like it went like this, down like this, right? Came up like this, came like this, came like this, came like this, right? And now the next one's going to what? Do this, like that. And then we should be back at the stop. Or it should, after that, just repeat itself. So let's go 2 pi now. This should give us the full picture. And now everything after that should just be the same thing. So if I now extend it out to 6 pi, we shouldn't see any difference. See? So this is definitely, I mean, stepping away from everything again, this is definitely not a function in the traditional sense of vertical line test, right? It fails vertical line test, but because we're in polar, it's a polar curve, it is a function. And so we can talk about the derivative and, all these other things. And that's where we're headed now. So let's talk about tangents to polar curves. So we do this kind of the way we did this before. We want dy dx, right? We'd like to know dy dx. That's the slope of the tangent line. This is now going to be looked at as being dy d theta over dx d theta. That's what we did last class also, right? But we were doing parametric. So what we did was dy dt, dx dt. Here we're doing theta because theta is our variable, our independent variable. And now the question is, what's dy d theta? So let me do this on the side. Remember, what was x and what was y in Cartesian to polar? X was r cosine theta, and y was r sine theta, right? So if I ask you here, hey, what is dy d theta? That means I want you to take the derivative of y over here with respect to theta. Let's do that right here. Take the derivative of y with respect to theta. Well, the question is, do we treat r like a constant, or do we treat it like a function? So is this just going to be r times the derivative of sine, or is it going to be product rule? What do you think? What is r, though? What is r? Isn't r a function of theta? Isn't it? Because remember, we said a polar curve is r is f of theta. So what we actually need to see this as is this is like a function of theta times sine theta. So we will not treat r like a constant, which means if we want the derivative of y with respect to theta, we must do product rule. And the derivative of a product is what? So y prime is derivative of the first, f prime theta, times the second, plus the derivative of the second times the first. Well, we'll have to be given that curve, right? They'll give us the r equals the function of theta. They'll give us that, and then we'll have to take derivative of it to figure out this. Y'all see how that works out, though? And then same process for x. What's the derivative of x going to be? So f prime theta again, cosine theta this time, minus sine theta f of theta. So product rule there. Now, I'm trying to get to this formula, so I'm going to come back down here and rewrite it. We have dy d theta will be our f prime theta sine theta plus cosine theta f of theta all over f prime theta cosine theta minus sine theta f of theta. That's it. Now the book does a slightly different formula from this. They don't use f prime theta. They just say r prime and r. So if you want, you can do that also. I'll put it underneath here. Or you could have r prime sine theta plus cosine theta r all over r prime cosine theta minus sine theta r. In either case, that is the formula needed to figure out the slope of the tangent line to your curve, which means you'll have to know theta and r, right? You'll have to know them both. That'll give us slope of the tangent line. Yeah, and they'll give us r. So let's do an example. You all ready? As an example, let's find slope of tangent to r equals 1 plus sine theta. That's that cardioid at pi over 6. Plug and chug. dy dx is equal to, okay, r prime. So what's the derivative of r here with respect to theta? Just cosine theta, right? So cosine theta, but then times, the formula says after that, what's after that? Sine theta plus cosine theta times r, which is 1 plus sine theta. Does everyone see where everything there comes from? We have r prime, this is sine theta plus cosine theta, and then this is r. See it? Okay, all over r prime again, so cosine theta times cosine theta minus sine theta times 1 plus sine theta. Yeah. Well, we can see if anything cleans up, but looking here, don't really see anything cleaning up. Well, if it were a plus, it would. Sine squared plus cosine squared. It would have to come out of both terms, so it wouldn't. You could say this: 2 cosine theta sine theta plus cosine theta. So all I did there was distributed the cosine through to the 1 in here, and then cosine theta sine theta is the same as cosine theta sine theta. Add them together, we get 2 of them. Then you have the cosine theta. On the bottom, it would be cosine squared theta minus sine squared theta minus sine theta. But I can't factor, see if I factor a negative out, then that would turn that first one into a negative. And so it still wouldn't be the Pythagorean identity. But that's okay, I mean, because all I have to do now is plug what into this? Pi over 6. So plug in pi over 6. So at pi over 6, you'd have to figure all those out. I really don't feel like doing that. You think you could just plug pi over 6 and all that? At theta equals pi over 6. All right, I'll do it. I'm not going to compute it all out. What's cosine of pi over 6? Root 3 over 2. Sine of pi over 6 is 1/2 plus root 3 over 2 all over cosine of pi over 6 was root 3 over 2. We're going to square it. That's 3/4 minus 1/2 squared is 1/4 minus 1/2. And then you just clean it all up. It's going to be an irrational number. Is it? Yes. Well, what we just found then is, this accidentally happened. I'm glad you pointed that out. I mean, what would happen here is we'd have division by 0, wouldn't we? Which means what? No. The slope of we're saying the slope of the tangent line is undefined, which means it's vertical. Not a minimum necessarily, no. It's a vertical. Go back to that. Go back to the cardioid. What was our cardioid? It was 1 plus sine theta. What we just found was if you go to pi over 6, which is about here, 30 degrees, we actually found this point's tangent line, which is vertical. You see that? I just happened to pick the wrong damn point. I mean, not wrong. I mean, The slopes, I mean, we have a tangent line. Its slope is undefined though, so it's vertical. Had we gone pi over 6, which is the book does, had I done pi over 3, which the book does, they get this in the tangent line here, the slope is -1. But I just happen to pick this one. Of what? What? What are you talking about? What are you talking about? Polar plot, Fibonacci, round phi. I'm not sure. Let me look at it. Well, we're not going to get into Fibonacci right now. Round. I'm not sure what round is though. Fibonacci. I'm not sure when they say Fibonacci. I'm not sure they're calling a function Fibonacci, but I don't know what that Fibonacci function's doing. So I don't know. I can't answer that right now because I'm not sure what the Fibonacci function's doing. Yeah, it is interesting, but all right. Let's stay on topic here, though. Okay, so the next question I was going to ask is where is the tangent line 0? Where's the slope? So you set it equal to 0, right? So you have to set the top to 0. So could we do that? If I said where is tangent horizontal, then you'd set the numerator equal to 0. And so you'd factor out a cosine theta. You'd be left with 2 sine theta plus 1 equals 0. And you may remember doing equations like that in pre-cal. You set each of those equal to 0. And the other equation, when you set it to equal to 0, you get sine theta equals 1/2. Where are all the places that cosine is 0? Theta is pi over 2 plus k pi or n pi. That means pi over 2, well, pi over 2 and 3 pi over 2, right? But you could start at pi over 2 and just add half rotations and keep adding half rotations, and you get both those points. And then where is sine 1/2? Here and here. That's pi over 6 plus 2 pi k, and then 5 pi over 6 plus 2 pi k. Because to get from this point back to itself would require a full rotation to get back to it. Was it negative? Oh shit, it was negative. But same principle. So well, I'm glad you're paying attention. I'm not all coherent today. No excuses. Yeah, this equation should be negative. Do y'all see that? 2 sine theta plus 1, take the 1 to the other side, divide by 2. That does change these answers, though. It's negative pi over 6, and this one would be 7 pi over 6. But did I answer your question as to why it's 2 pi k? All right. Okay, let's move on because it's really not, I want you to be able to apply the formula and just know about it. Solving these equations and stuff, that's pre-cal stuff, so I don't want to spend too much time on it. Next thing. The derivatives we've got. See if there's anything else I want here. Let's move on to the next section, 9.4, areas and arc lengths. So areas of polar curves. So if you take that example that we had a second ago where it drew, we had it and it was drawing all the different leaves on petals on a flower or something. Oops, sorry. Where the hell is that? Forgot to turn it off. Right, we would maybe want to know what the area of one of those or all of them are. So let's look at one first and then we'll go after it. How about we'll go here and let's do sine, you want to do sine 2 theta? There we go. What if we wanted to know the area of one of these petals? Then we just multiply it by 4 to get all, right? So let me first restrict this from, what do you think it would be? 0 to what? What do you think would draw just that first petal? You want to try pi over 2? Something happened here. Where? There we go. Try that. Did I remove it on accident or something? There we go. Okay. 0 to pi over 2. There we go. So what I want you to imagine we're going to do is I'm going to take that picture and put it on my notes and I'm going to draw something in it and let's talk about it, okay? So taking that petal, just in that first quadrant here, taking that petal, imagine we want to take a slice of it, okay? But because we're in polar, we can't take rectangles because there are no rectangles in polar. Everything looks like a polar region. What I mean by that is, remember when I was doing that earlier, right in the beginning, and I showed you what a rectangular polar region looked like, as opposed to, it's got to have arcs to it. So what I'd like to do is imagine just moving to an arbitrary angle. Just like we used to pick an arbitrary X and draw a rectangle, I'm going to pick an arbitrary angle. Here it is, just that, but there it is. Got my rectangle. Go out here like this, and I've got my angle. Go out like this, and that should correspond to some point on my curve, right? Now, I'm going to do a dx. Remember dx used to be the width of the rectangle? I'm going to do, instead of dx, a d theta, which is going to just change my angle just a little bit to give it some width, right? So I'm going to exaggerate it and make it look very large so I can draw it. That's my d theta in here. All right? And then I'm going to attach the two endpoints with the curve. So it's almost like I took that little point here and I swung it through an infinitesimally small angle. Do y'all see the relationship? I really hope you do. Between this and what we've done before, where we came out, we picked an arbitrary X, we drew a rectangle, we said, okay, we'll give it some width, right? We'll call that width dx. And we knew that there would be some error, right, in that approximation. Same thing here. I go out to a certain point on the curve, I give it some width, d theta. I know there's going to be some error because the curve may not arc just like that green does. It may go out a little bit or change. It may not be a perfect arc. But this is a good approximation because as I go and do infinitely many of those, it'll converge to the correct area. Does that make sense? The only thing left to figure out is what's the area of that? What's the area of the green? Well, r is the radius, right, from here to the edge. That's r. So I really just need to make sure everyone here understands what the formula for this is. If you have a radius and you have some angle, this is r, and this is, I'll call it d theta still. The area of this is what? Well, if you go back to pre-cal, you were taught, hopefully, a formula for the area of a sector. Anyone ever see this before? If you take a radius, you swing it through an angle theta, the area of this is 1/2 r squared theta. That's the formula for it. And it turns out that if your angle is all the way around, then what's your angle? 2 pi. If you plug 2 pi in there, what do you get for theta? You get pi r squared, which is the area of a circle. This is like the more general formula for the area of a circle. The formula for the area of a circle comes from that formula. So we need to know that, okay? This we have to, we're kind of given that formula. And because of that, if we come back up to our green one, then the area should be what? It should be 1/2 r squared d theta. And what do we want to do with that little sliver to get the area of it all? Add them all up, right? Forever infinitesimally small. That's an integral, isn't it? So we want to integrate 1/2 r squared d theta from where to where? Well, it'll depend on our problem. In this problem, it'll be the angle we started at to the angle we ended at, which was 0 to pi over 2 for us. Yes? So here's the formula. I'm going to stick the formula right up here with this. The formula that we have is we'll have the integral, and we'll call it alpha and beta. Is that okay? Alpha to beta. 1/2 is going to come out, r squared d theta. And remember that r, right, is really f of theta, isn't it? So that'll usually be given to us. Do you see where it comes from, though? It's pretty cool. Next thing is going to be an example. So as our example, let's find the area of one loop of r equals, it was sine 2 theta, right? That's what we did. Oh, by the way, before I forget, your calculators have parametric mode. They also have polar mode. So you can graph polar equations on your calculators. You might want to practice doing that, because on your test, if I ask you to graph one loop of something, you're going to need to know the most difficult thing for you is going to be the limits of integration, is what your theta is that draws that loop. That'll be the hardest part for you. So for this one, I know I'm talking about this loop here. Therefore, my alpha is equal to 0, and my beta is equal to pi over 2. I'm going to have 1/2 the integral from 0 to pi over 2 of the function sine 2 theta, but then squared d theta, which is just 1/2 integral 0 to pi over 2 sine squared 2 theta d theta. How are you going to get that integral? I'm hearing lots of different. Power reduce. 1/2 minus 1/2 cosine 4 theta. So you'd power reduce that and then go from there. Okay? Think you could do that? All right, last thing, and then we can talk about the final. Arc length. Okay, do y'all remember with arc length we had a formula with parametric that the length was equal to the integral a to b square root dx dt squared plus dy dt? If you look back in your notes, you should have that. That's what we had. Well, what we need to realize is that when we have these parametric equations, or no, I'm sorry, when we have these polar equations, right? Those are our polar equations for x and y. If r is a function of theta, then you could just change all your thetas to t's, just use a different variable. And what you have now are parametric equations, right? Parametric equations meant you had x was a function of t and y was a function of t, right? That's what it was. Do you all see what I'm saying or not? So what we would need to do is take the derivative of each of these, square them, and plug them in up there and see what it would look like. So let's take derivative of x here. What's x prime? Well, that would be product rule, right? We just did that. F prime t cosine t plus, minus yes, hold on. It doesn't matter which order, right? Ah, shit. That's what the derivative of that would be. Derivative of y would be f prime t sine t plus cosine t f prime, or ft, which we said was r's, right? Those were r's. So we did that a little while ago. But now we square them. So I'm going to take a moment to square these. I think I'll switch to r's, though. I'm going to say r prime cosine t minus sine t r. Let me square this now. That's r prime cosine t minus sine t r squared. When you square that, wouldn't you get r prime squared cosine squared t minus 2 r prime sine t cosine t plus sine squared t r squared. Jesus. That's what you would get if you squared that. What about y prime? Y prime was r prime sine t plus cosine t r. If I square that, I would get kind of the same story. It's r prime squared sine squared t plus 2r prime sine t cosine t plus cosine squared t r squared. What a pain, right? I mean, I understand I'm working through that kind of quick, but I'm just showing you where this formula comes from. And now, in the formula, look back up here, what am I supposed to do with the derivatives squared? Add them. So let's just take the two answers we just got and add them together, and let's see what happens. So I'm saying take this and add it to this. And what you get is these cancel, right? What's these two together? Those both have r squared in them, right? So factor out an r squared, and you're just adding the sine squared t to the cosine squared t. Sine squared t plus cosine squared t is 1. So that's just an r squared. And then isn't this the same thing over here? So you just get r prime squared. That's it, right? And that's underneath the square root. Same thing, you just factor out an r prime squared, factor it out, and then sine squared plus cosine squared is 1. Which brings us to our final formula, and that is that the length of an arc for a polar curve is equal to the integral from, now, t was our variable before. We switched theta to t. So we're going to switch it back now. So we'll go alpha beta, square root, and we just got r squared and r prime squared. So we're just going to say r squared plus r prime squared, and then d t, but we're going to say d theta. That's it. Example time. Find length of cardioid. R equals 1 plus sine theta. So what did I say was going to be the most challenging part for the area, and now I'm saying for arc length also? I mean, you know it's going to be an integral. You know you're going to have a formula for it. Well, even before that, figuring out your endpoints, alpha and beta. So what is the limit on theta that gets you to draw the cardioid? So you might, if you have your calculator, you might want to take this time to see if you can figure out how to draw in polar mode. And I'll do it too, because I haven't done polar mode on this thing in a long time. Oh yeah, look at that. 1 plus sine, but you have to use theta variable, right? Where the hell's my theta variable though? Well, on your calculator, but not mine. 289. That's kind of crappy. Oh, there it is. I see it. Window. Okay. Anyone need help? Anyone that has their calculator need help? Did you draw a cardioid? You got it? Good. Yep. Okay. Invalid dimension. Do you have anything on this calculator that's okay? I would just, anytime that happens, just like clear your memory. So above here, just do, well, quit that. Um, Reset all around. Okay, so now go mode, go polar, go graph, y equals. So try it again. Yes? So you know what I would try for you is to get your limits on your theta, change your window to only go from 0 to pi. 0 to pi. It should only draw half the cardioid, but not the half you think it would be. It only draws the top. Yeah, it only draws something. It only draws that. So it doesn't draw like the right half or something. Did it work? Okay. Theta step is just like your d theta. See, your calculator is drawing a bunch of points, and if you make your theta step a large number, it'll look jagged. Yeah, because mine was 0. Changed it to match his. When it was 0, it was all crazy. Yeah, because it's not supposed to be 0. Yeah, make it 1. Watch, if you make it 1. See, what it does is it changes your theta by 1 each time, and then it connects each of those dots with a straight line. So it looks like a polygon. All right. So we know that it's from 0 to 2 pi, right? So we're going to try and do the integral from 0 to 2 pi, because that's what drew the whole thing. I had to look at my window, though, to see. My window said my theta min and my theta max. My theta max was 6 point something, which is 2 pi. That's how I knew. That's the only way I'd know. Yeah, if it's a leaf deal and you want to see which, what your theta needs to be to get that one piece. If you did, that would have been okay. But they only wanted one leaf, so yeah. But on that leaf, if I ask you for one leaf and you go 0 2 pi and give me what all 4 or 6 leaves would be, then that wouldn't work. You need to know where that one leaf is and what the theta restrictions are on that one. Does that make sense or not? Okay. The cosine. Mm-hmm. We can revisit that because let's talk about that because that's going to change. Let's do that after this one. We'll look at that one. Okay, so what I need in here is I need the derivative squared and the function squared, right? So what's the derivative of r? Cosine theta. And I need to square it. So r prime is cosine theta. R prime squared is cosine squared theta. So in my formula, I have r squared, which is 1 plus sine theta, squared plus the derivative squared cosine squared theta. And then d theta. What is 1 plus sine squared? What is 1 plus sine quantity squared? 1 plus 2 sine theta plus sine squared theta plus cosine squared theta, d theta. So, yeah, those become 1s. So 0 to 2 pi square root of 2 plus 2 sine theta, d theta. And you could factor out a 2? Okay. But at this point, we're going to stop. The book carries this, or talks about the rest of the way on page 527. Again, what I'm going to be looking for is that you get to this, and I'll either tell you stop at the integral, or I'll tell you it'll be something that'll be doable. This one's not very easy. Again, application of the formula is all I really want to see on these last few sections. There was a question to look at a different polar curve. You want to look at cosine? So let's see, cosine theta. Okay. Like this? Great question. If I wanted you to give me the area of one of those leaves, or even the arc length of one of those leaves, you would need to be able to figure out the most difficult part for us will be the limits of integration. Can't go 0 to pi over 2 because here's 0, here's pi over 2, and your leaf is not there. So where would you have to go from? Pi over 4 to, well, there's 4 leaps, right? So there are 4 equal. Look, draw an x and a y axis here. Like, I mean, this is 90 degrees between these two, right? 90 degrees, 90 degrees. So this leaf, since this one's cut in half and half, that would be 45 degrees, right? That's 90. This would be 135. So this is your pi over 4, and this would be 3 pi over 4. So you'd integrate from pi over 4 to 3 pi over 4. Does that help? Yeah. But you'd have to recognize that. Now here's another one. To get that for that one, yes. But then if you have something like this, now look at that. So you could go from pi over where to pi over what? Other way around. Okay, so one leaf here. You said pi over 3 to pi over 6, but pi over 3 is bigger than pi over 6. Okay, that's what I meant the other way. Do you all agree? Now you have me saying it. Pi over 6 to pi over 3? You could count the number of leaves, 1, 2, 3, 4, 5, 6, 7, 8, right? Is that 8? Would that work to count by 8 though? Not really. Then you're just doing it by looking? How many full leaves are there in the first quadrant? Yes, there's one, but I mean this half and this half together, you would say what? There's really two in there, or you could say that's split equally. I agree. Pi over 6 to pi over 3 would be right, but you just have to be careful with this. What would be more powerful for you is to find a general formula. I'm not going to push it this hard, but look at that. See, that one's a little more challenging. Oh yeah, I see what you're saying. Could you just go like pick something in here and no, you can't. Because when you're over here, you're actually in here. So you'd be picking up pieces in here. Yeah. It's your radius is not 0 all in here. Your radius is way down close to 0, but it's not. It's only 0 at, maybe one particular angle. So now I won't give you anything like that, okay? But that's kind of what you try to lead yourself to a more general way of attacking these. I think we're good. See, I don't think that there's anything else. Now, I did, we're actually pretty much, I mean, that's pretty much chapter 9. There's conic sections in chapter 9. One more section, that's it. Chapter 10 is where Cal 3 starts. So, we're officially done. You saw everything I wanted you to see, at least. This is the review that I posted. You already got one? We're going to have a few extras there. There's 3 there. Let me just have one of those, please. Okay. So I was so sick. I was sitting there going, but I need to get an idea of what to give you all for the final. And lo and behold, I found this review from last time I taught it. And I thought, man, that's pretty good right there. That's a pretty good little review. So we'll talk about it in a second. But I told you you could have the sheet that had the Maclaurin series on it. So I printed you out a copy of it right now. Okay, here you go. And it has the rest of the stuff from that page, including part of an example. So I would like for you to take that off. So cut this out later, okay? All right. I'll let you use this. Just cut the table out. I didn't have time to do it myself. I don't think it would make that much of a difference, the example that's below, but still. There should be 4 there. Okay. All right, let's talk about this review. I will post the answers to this later. I'm not saying today, but at some point I will. I mean, technically anything we've done is fair game, but these are the things that I would focus on. Finding the area between 2 curves. I mean, that's just pretty clean. There's nothing crazy there. Find the volume of a solid obtained by revolving the region bounded by y equals x sine x, x equals 0, x equals pi, y equals 0 about the x-axis. So you need to know the formula for that, for doing solids of revolution about the x-axis. You need to have a good drawing of the region, and then find the volume. You'll notice, though, in that integration, you're going to have to integrate, you're going to wind up having to integrate the function y equals x sine x, which requires, anyone know how to integrate x sine x? Integration by parts. Good. Find the length of the curve. Do y'all notice next to each of these problems I have like 7.1, 7.2? That's the section this is coming from, so you can go back and look at it. Find the surface area generated by revolving the curve, y equals x cubed, blah, 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 about the x-axis. We had a formula for that. Yeah. Okay, number 5, evaluate the indefinite integral. So you have, improper, you have it in, why did I say indefinite integral? I don't know, man. My brain's just not here. Okay, so yeah, on that one, to integrate it, you're going to have to, what, probably partial fraction decomposition? Turn it into 2 integrals, and then let you know, one of them go to infinity after you take the antiderivative, see what happens. Well, yeah, don't mix it up with series, though. Yeah, okay. And then number 6, evaluate that. What I want you to notice is that there's a discontinuity in the interval. So look, it goes from 0 to 5, but your function is undefined at 2, which means you have to break it into 2 different integrals. One that goes from 0 to 2, another one goes from 2 to 5, and then figure out what happens with each one of those. Again, it's from 6.6. Take a look. Then we start with chapter 8. So yeah, there was some chapter 6 in there. Someone had said just 7 and 8. There is a little 6 in there. 7, number 7, find the sum. Anybody recognize that series? Yeah. If I say find the sum, that means it does add up to something, which means it converges, right? Which means it's either geometric or telescopic. Well, that one's geometric, so have fun. So that means you're going to have to find the formula, figure out what your A is, figure out what your R is, and then use A over 1 minus R. But I'll tell you right now, A is not 2 in that problem. Well, hold on. Is it? N equals... What's our formula for geometric? Sum n equals 1 to infinity A R to the n minus 1, or sum n equals 0 to infinity of A R to the n. I think, well, is it that? Is it really? It is that clean. That's not even, I didn't even challenge you on that one. A is 2, R is 1/3. I didn't think I put something like that on there. Okay, well, you shouldn't be surprised that on a final, it would require you to do a little bit more work. Like maybe, you know, instead of 2 plus 2/3 plus 2/9, it would have been 2 over 3 plus 2/9 plus 2/27, where you'd have to peel off something to redo your A. Do y'all know what I'm saying or not? In any event, it's geometric series. All right, you need to be able to find the sum of a geometric series. Number 8, find this sum. That's telescopic. So you have to do partial fractions. 9, I actually tell you what test to use. Use the integral test to determine if the series converges or diverges. Number 10, use the comparison test to determine. So, I don't know, would y'all like for me to tell you what test? I guess so. Yeah, I think at this point, use the limit comparison test to do number 10. So you should be able to do comparison and limit comparison for number 10. test paper on your what? With all the tests. Oh, yeah, yeah. Let's talk about what you can have after I'm done with this. Okay, number 12. Use alternating series test. 13, absolute convergence test. If the absolute value converges, yes. Yeah, but, wait. What's theorem 8.4? Is that theorem 8.4? You sure? Okay, whatever. I've already done the brain dump. I've already done my brain dump for the semester. You get to do yours after next week. Okay, yeah, on number 13, you have to be careful because you can't just take the absolute value of that and be good, because you have to do a little bit of a comparison. Yeah, almost like the squeeze because of the boundaries, because it's not an alternating series. It's not alternating. That's right. Okay, number 14. Find the radius of convergence and interval of convergence. So, what are you going to have to do to find the radius of convergence and interval of convergence? Ratio test. And when you do that ratio test and things start to cancel, you figure out what's going to happen. And then that has to be, whatever that is, has to be less than 1. And then see, if you're lucky, when n goes to infinity, it squashes down everything to 0, but I doubt that's going to happen. So that'll give you some restriction on x. Just be careful with all your absolute value stuff there. Then you create your intervals. And because I'm asking for the interval of convergence, that means you must test the endpoints. If I don't ask for interval of convergence, you do not have to test the endpoints. So number 14, you'll have to test endpoints. 15, find the power series and radius of convergence. Means all you have to do is find the power series first, and then do your ratio test and just get your absolute value of x is less than 2, and then your radius is 2. You don't have to test endpoints. What would you use for number 15 to try and write that as a power series? You would need to use this very important power series. Remember that? Right. So number what? 16. 15. 15. 15. Oh, I'm not saying that 16 is not that. I'm just saying 15 is that for sure. You have to make it look like a 1 over 1 minus u. But you got to pull that 2 out of there, and then rewrite the 3 as a 3 halves, and then make it a negative, and then you write out that power series, and you find its radius of convergence. Number 16, write the power series for 1 over 1 plus x squared. Yeah, that's right. You have to recognize that 1 over 1 plus x squared is the derivative of something. So yeah, and we did a couple of those. Number 17, find the Maclaurin series for x cosine x using the definition. That means you're not allowed to use the table that I gave you. That means you have to write out the derivatives, find a pattern, and then start writing out the series. And I only ask for, well, no, I don't ask for anything. That's what I want. Number 18, find the Taylor series of e to the 2x at a equals 3. You cannot use your formula sheet for that because your formula sheet only works for Maclaurin series. So that one you're forced to do by hand. Number 19, approximate that by integrating the first. We really didn't do much approximation, so you can scrap 19. Number 20, I did in class last time. Given x equals, so this is now starting chapter 9. Given x equals t minus t to the negative 1, why is that? Find dy dx. Given x equals t minus blah, blah, find, whoa. That's the same problem? It is? Okay. 21, find the area enclosed by the parametric curve. 22, find the length of a parametric curve. I think we did that one in class last time also. 23, find the derivative dy dx at theta equals pi over 6 for r equals 2 sine theta. That's what we just did today. 24, find the area enclosed by one loop of 4 cosine 3 theta. What's not on here is arc length, because I don't think I covered arc length this spring semester. I taught this. So just throw an arc length on there at the end. So you could just say number 25, find the length of one loop of r equals 4 cosine 3 theta or something like that. Find the length of one loop. That's it. Oh my gosh, it's time. What are you going to be able to bring to the test? You can have this, what I just gave you. You can have the tests. What are those? Those convergence test sheet. You can have that packet of all the different formulas, right? Well, hold on. So that's 3 things so far, right? This thing, Maclaurin series, the convergence tests, the derivative packet stuff, and then one 8.5 by 11 sheet of paper with whatever else you want to put on there without worked out problems. So any other formulas, steps, procedures that you want, just don't have problems worked out. So all your polar area, arc length, parametric formulas, you know, Cartesian to polar, you know, all that stuff, throw it on one sheet of paper. Any questions? When is our final? Tuesday? Sucks. I mean, yeah, but if you wanted more time, you know. Tuesday at 11, yeah. I can't make that change. We're good. Okay. Anyone have questions? It's going to depend on how I feel. Yeah, I mean, my plan is to be, because I've got meetings.